Have you ever stopped to think about how much light shapes our world? It's truly amazing. Light allows us to see the beautiful colors of a rainbow, helps plants grow, and even carries the information for our super-fast internet. For centuries, scientists and engineers have been trying to control light. We use lenses and glasses to help us see clearly, and mirrors to change the direction of a light beam. But what if we could control light with something incredibly thin, almost invisible? This is where a super exciting field of science comes in: metasurfaces. These aren't your everyday materials. They are specially designed surfaces that can do extraordinary things with light. Imagine a material so thin it's almost two-dimensional, like a single sheet of paper, but covered in millions of tiny microscopic antennas. Each of these nano antennas is smaller than a wavelength of light. That's how small we're talking. By carefully arranging these tiny structures, we can tell light exactly what to do when it hits the surface. We can bend it, focus it, or even change its color. Metasurfaces are like a traffic control system for light waves, directing them with incredible precision. This opens up a whole new world of possibilities for technology, far beyond what we can achieve with bulky traditional lenses and mirrors. Controlling light is one of the most important challenges in modern science. Think about our smartphones. The camera bump on the back exists because it needs a stack of curved glass lenses to focus light onto the sensor. Metasurfaces could replace that entire stack with a single flat layer, making our phones thinner and lighter. Beyond just our gadgets, controlling light is crucial for creating more efficient solar panels that can capture more energy from the sun. It's also key for developing faster communication systems that can transmit more data through fiber optic cables. Essentially, mastering light means unlocking a more powerful and efficient future for everyone. So, what makes these metasurfaces so special? It's all about the interaction between light and these tiny engineered structures. When light, which is an electromagnetic wave, hits these nano antennas, it gets scattered in a very specific way. By changing the size, shape, and arrangement of these antennas, we can precisely control the phase and amplitude of the light that passes through or reflects off the surface. This is a huge leap from traditional optics, which relies on the slow accumulation of phase changes as light travels through a thick piece of glass. Metasurfaces give us a powerful new toolkit to manipulate light in ways we've only dreamed of until now. For a long time, scientists used noble metals like gold and silver to build the tiny antennas on metasurfaces. These metals are great at interacting with light, especially in the visible spectrum, which is the light we can see. This interaction is thanks to something called plasmons, which are collective oscillations of electrons on the metal's surface when they are hit by light. Think of it like a ripple spreading across a pond, but with electrons instead of water. This effect makes gold and silver really good at concentrating light into tiny spots, which is perfect for building nano antennas. They were the go-to choice for early experiments and helped prove that the concept of metasurfaces could actually work. However, these shiny metals have a big downside. While they are great at interacting with light, they are also a bit too good at absorbing it. A significant portion of the light that hits a gold or silver metasurface gets converted into heat and is lost. This is a major problem if you want to build an efficient device, like a super thin lens. You want as much light as possible to pass through and be focused, not get wasted as heat. This energy loss, known as ohmic loss, means that devices made with these metals can be inefficient and can even overheat, which is not ideal for sensitive electronics or high-powered applications. This is where a new class of materials comes to the rescue. Scientists started looking for alternatives that could interact with light strongly, but without the same energy loss. They found fantastic candidates in materials like titanium nitride and various metal oxides. These materials, often called refractory materials, are incredibly durable and have high melting points. More importantly, they behave a bit like metals in terms of their optical properties, but are much less lossy, especially in the visible and near-infrared parts of the spectrum. They offer a much better balance, giving us the strong light interaction we need without paying the price of high energy absorption. The switch to materials like nitrides and oxides has been a game changer for metasurfaces. They are not only more efficient, but also more robust. Gold and silver are soft and can be difficult to work with on a nanoscale, but materials like titanium nitride are hard and stable, making them easier to manufacture into complex shapes. This durability also means that devices made from them can withstand higher temperatures and more intense light, which is critical for applications applications like high-power lasers or devices that operate in harsh environments. By moving beyond traditional metals, we are paving the way for metasurfaces that are not just clever, but also practical and reliable for real-world use. So, how do we actually make these amazing metasurfaces? It all happens in a clean room, a super clean laboratory environment where even a single speck of dust can ruin the process. The fabrication is a bit like nanoscale three-dimensional printing. Scientists start with a flat, transparent wafer, often made of glass or silicon. They then deposit a very thin layer of the chosen material, like titanium nitride. Using a technique called lithography, they project a pattern, like a blueprint for all the tiny antennas, onto the surface. Then, they use chemical or physical processes to etch away the material that isn't part of the pattern, leaving behind millions of perfectly shaped nanoantennas. Each of these nanoantennas is carefully designed to manipulate light in a specific way. By changing an antenna's shape, making it a cylinder, a rectangle, or even an L shape, we can change how it delays the light passing through it. This delay is called a phase shift. To create a lens, for example, we need to delay the light more at the edges of the lens and less in the center. With a traditional lens, this is done with a curved piece of glass. But with a metasurface, we can achieve the exact same effect by arranging antennas of different shapes across a flat surface. Antennas on the edge will be designed to cause a large delay, and antennas in the middle will cause a small delay, perfectly focusing light to a single point. Let's go back to the camera in your phone. The camera module is thick because it uses a series of curved plastic or glass lenses to capture a sharp, clear image. Each lens corrects for different kinds of optical errors or aberrations. A metasurface can do all of that work with a single flat layer. By programming the correct phase pattern into the metasurface, by designing all the millions of nanoantennas just right, we can create a metalens that is not only flat and thin, but also corrects for aberrations more effectively than a stack of conventional lenses. This could lead to cameras that are no longer bumps on our phones, but are seamlessly integrated into the device. This ability to shape light goes far beyond just focusing it. We can design metasurfaces to do all sorts of incredible tricks. We can create holograms that project three-dimensional images into the air, far more complex and detailed than the ones you see on a credit card. We can also build devices called spectrometers on a chip, which can analyze the color composition of light to identify different chemicals, useful for everything from medical diagnostics to environmental monitoring. The beauty of metasurfaces is their versatility. By simply changing the design of the nanoantennas, we can create a device that bends, splits, focuses, or filters light in almost any way we can imagine. One of the most exciting frontiers for metasurfaces is making them tunable. This means we can change what the metasurface does to light in real time after it has been made. Imagine a pair of glasses where you could adjust the focus just by thinking about it, or a camera lens that could zoom in without any moving parts. Scientists are developing ways to do this by integrating new materials with the metasurface. For example, by applying a small electrical voltage to a metasurface made with special materials, we can change the optical properties of the nanoantennas, thereby altering how they bend light. This would make devices like microscopes or virtual reality headsets dynamically adjustable. These new materials also make our optical devices much faster and more efficient. In communications, data is often sent as pulses of light through fiber optic cables. Modulators are devices that turn the light on and off very quickly to encode information. Metasurfaces made from tunable materials can act as incredibly fast modulators, switching light at speeds far greater than what is possible today. This could dramatically increase the speed of the internet and our data networks. Furthermore, because these metasurfaces are so thin and efficient, they use much less energy, which is a huge benefit for everything from handheld devices to massive data centers. Controlling how materials absorb and emit light is also fundamentally important for many future technologies. For energy, we can design metasurfaces that are perfect absorbers of sunlight, capturing every possible photon and converting it into electricity for ultra-efficient solar cells. We could also design surfaces that are perfect emitters of thermal radiation at specific wavelengths, which could be used for passive cooling systems that radiate heat away into space without using any electricity. This level of control is also crucial in the strange world of quantum computing, where single particles of light, or photons, can be used as quantum bits. Metasurfaces could help us create, manipulate, and detect these single photons with unprecedented accuracy. In conclusion, metasurfaces and the new materials used to build them are set to completely revolutionize our relationship with light. They represent a shift from the bulky, static optics of the past to a future of flat, dynamic, and incredibly powerful optical systems. From making our smartphones thinner and our internet faster to enabling breakthroughs in renewable energy and quantum science, the impact of these tiny engineered surfaces will be enormous. This isn't just a small improvement, it's a whole new way of thinking about how we build with light. The future of technology is looking very bright, and it's being built one nano antenna at a time.